Welcome to our session, How Amazon Migrated a Large E-commerce Platform to AWS Graviton. I'm Frank Stone, and I'm a Principal Solutions Architect with Amazon Web Services. I work with our internal Amazon teams to leverage and adopt AWS services. And joining me today is Sean Connell. Sean's a Principal Software Engineer with Amazon.com and works on the DataPath team, which is one of the largest backend platforms powering Amazon.com. And they've transitioned tens of thousands of instances to AWS Graviton with increased performance and reduced costs. Some of the areas we'll cover today will include Graviton, its benefits and architecture. We'll share details about the DataPath platform and DataPath's transition, including the software updates that were needed and the testing approach that was used to optimize and validate the deployments. We'll learn about the migration approach that the DataPath team used for their production deployment to Graviton and the results. And finally, we'll share some resources you can use to realize similar benefits with AWS Graviton. Now here's a picture of the actual AWS Graviton 2 chip. This is developed in partnership with the ARM team and involves and uses 64-bit ARM Neoverse cores. And we've implemented targeted optimizations for cloud-native workloads. And the Graviton processor came from our focus on innovating to enable new capabilities for our customers. Here you see a picture of the original Graviton processor that we announced in 2018. It was the first ARM processor in AWS, and it is implemented in the EC2 A1 instances. It was built on a 16 nanometer process and has about 5 billion transistors. In a scale picture, you can see the Graviton 2 processor, and we've significantly upgraded it from our first implementation. This processor has 4 times the number of virtual CPUs, 16 rather than 64, and 7 times the CPU performance that we had in the original Graviton processor. That's about 2 times the performance for every vCPU. Now, it uses a denser new process, a 7 nanometer process, but it's a larger die, and so it has 30 million transistors, which allows us to onboard a lot more capability onto this processor. Now, the Graviton 2 is the core of our instances, but it's not everything we have in our instances, and we have several other pieces of custom developed silicon that provide the overall capabilities for our Graviton 2 based EC2 instances. One of those pieces of silicon is the Nitro security chip. It's integrated into the motherboard of each server and protects and monitors the hardware resources. Then there's the Nitro card itself, which unloads many of the traditional software needs of the hypervisor onto its own hardware, allowing for much better performance of the hypervisor with a much lighter footprint. The Nitro card handles interfacing devices such as our storage devices, Amazon EBS or Elastic Block Store, or our network devices, Amazon Elastic Network Adapters or ENAs, and also provides additional monitoring and security for those interfaces. And finally, with the security chip, the Nitro card, the hypervisor can be very light, and it handles the memory and CPU allocation with bare metal type performance. These purpose-built and modular building blocks give the Graviton 2 based instances tremendous performance. But the real benefit for you is in the total cost of ownership with AWS Graviton 2. Now remember, the AWS Graviton 2 powered instances have the highest performance within their instance families, along with a 20% lower cost when compared to the same vCPU and memory configuration in those instances. Again, that leads up to a 40% better price performance versus comparable x86-based instances. And it provides the best price performance within each of the instance families and can lead to real savings for you. Another benefit of the AWS Graviton 2 processor is the power efficiency of the CPU. When tested with other CPU processors, it provides 3.5 better power efficiency or performance per watt than other CPUs. That results in lower power and higher density that we can provide in our data centers, which is lower cost to you. And better yet, it provides a lower carbon footprint, which is good for the environment. Now, in addition to the performance and cost savings with Graviton, there's significant momentum with the software support for Graviton. With out-of-the-box support for Linux distributions, including our own Amazon Linux 2, SUSE Linux Enterprise Server, Ubuntu, and Red Hat Enterprise Linux. AWS tools also support AWS Graviton, and you can use those tools if you're looking for Systems Manager, Batch, our Cloud9 IDE, or some of our DevOps services, Code Commit, Code Build, and Code Pipeline, and others. They all support Graviton. Beyond that, there's significant momentum within the larger software community for Graviton. And you can see here an example of databases such as Cassandra, MongoDB, PostgreSQL, MySQL, and others. Configuration and monitoring tools such as Honeycomb, Datadog, Chef, Terraform, Splunk, security tools such as CrowdStrike, and build and test tools such as CircleCI, GitLab, Jenkins, and others, all supporting Graviton natively. There are also multiple AWS services that provide the opportunity to benefit from Graviton and the Graviton 2 instances with similar or larger improvements in price and performance. Those include RDS and Amazon Aurora for databases, Amazon EMR for Hadoop and Spark implementations, Amazon Elasticache with Memcached and Redis, Amazon OpenSearch, and most recently, Amazon Lambda, which provides up to a 34% better price performance over the x86 Lambda instances when you go with the Graviton instances in Lambda. Now I'd like to share some of the design decisions we made in the AWS Graviton design to enable the benefits that I've described. Now I've mentioned the cores, which are ARM Neoverse N1 cores, and we work closely with the ARM team on the creation of those N1 cores, bringing in our learning from running cloud-native workloads in AWS. Some of the things that we did is we added large caches dedicated to each virtual CPU. There's a L1 64 kilobyte cache and a 1 megabyte L2 cache for each of the virtual CPUs. We've also added, which is unique for ARM processors, a coherent instruction set. And we've done things like lowering the overhead of interrupts, adding support for virtualization and context switching, which are common in cloud workloads. And we've added performance capabilities such as dual SIMD units and data types to accelerate the machine learning inference, such as int8 and FP16. In addition with the cores, something to note is that every virtual CPU in the Graviton 2 processor is a physical core. And we don't use simultaneous multi-threading, which is common on other x86 processors. And you can see in this chart here the implication of that. With the Graviton, you get consistent performance no matter how many cores you use in the processor because the resources are dedicated. You have a dedicated physical core, you've got the caches that I mentioned, and they're not contending for resources. But for processors that use simultaneous multi-threading, as you get to using more of the actual virtual CPUs on a processor, there starts to be contention and you see a drop-off in performance. So that's a significant benefit for heavy loads that use the Graviton processors. They can expect that consistency in performance. Another attribute of the Graviton 2 is the high-speed interconnect. I mentioned we had a significant amount of memory and cache and 64 virtual CPUs. And this gives, we have approximately 2 terabytes per second of bisection bandwidth that allows connectivity across that processor. In addition to that, and the private caches that I mentioned, there's a 32 megabyte last level cache on board the processor. So that, with the private caches, provides over 100 megabytes of user accessible cache. Another benefit is unlike most x86 processors, because of the connectivity that we have and having so much of the capability on board on the processor, we don't need to support non-uniform memory access or NUMA. And what that means is that for many of the applications which are not NUMA optimized, that just because of that, they see significant performance benefits when they move to Graviton. And another aspect of the Graviton is that it supports 4th generation PCIe, which powers our connectivity locally to things like the SSD storage that we have in our D variants of our EC2 instances for Graviton. With that, I'd like to turn it over to Sean, and Sean will share the details on DataPath and their transition of tens of thousands of instances to Graviton and the work involved and the benefits achieved. Off to you, Sean.
Thank you, Frank, for that introduction. Hi, I'm Sean, a Principal Engineer on DataPath for Amazon.com, and I'm going to tell you about DataPath's migration to Graviton, some of the things we learned along the way, and hopefully some tips for you in your migration. First off, I want to talk about why we were interested in Graviton. We have a lot of hosts inside of Amazon, tens of thousands of EC2 instances, which means any sort of hardware improvements that we can get will be a large change for the company's bottom line as well as our internal team. So when we were looking at that 40% number, it was too big to pass up. In addition, we're a hosted runtime service, and we host other people's code, which would normally make this kind of migration difficult. But because of our architecture, we had a few tricks so that we could move people's code without them worrying about the processor underneath them. The combination of this opportunity and this particular technical trick put us in a really good position to save a lot of money. I mentioned a little bit about how we run code, but what is that code doing? We have a lot of different use cases on and off the Amazon.com website. These are things around like, can I buy this item? What price is it? Who's selling it? Can I get it tomorrow? These use cases are all using our service to compute that answer for you, the website customer. So if you've used Amazon.com in the last 8 or 9 years, you've used the DataPath service underlying this data without knowing it. So that's kind of the basic product fit. I mentioned this kind of writing and hosting aspect now. Our clients, which are internal business teams, write their logic in a declarative high-level language. And this allows them to focus on the actual business logic, the value differentiated code about, can I get it tomorrow? They don't have to worry about implementation details like threads, memory management, or other such kind of low-level things. They also don't have to worry about as much infrastructure. They kind of just give us their code and we roll it out and host it on our service. We also deal with some things like metrics and alarming. And taken as a whole, all of these things mean that we control pretty much all of the software lifecycle on their behalf. This control gives us good ability to switch hardware without them noticing. So that's kind of the language piece of it. Now, the most interesting piece that we'll be talking about is the runtime. Now, of course, this is kind of where the implementation matters, right? This is the part that runs on the server that cares about things like Graviton or not Graviton. And it's a concurrent Java application. A lot of you probably also run concurrent Java applications, and these are kind of the old school bread and butter for a lot of different services out there. So it's Java. It's also non-blocking and non-locking, which is a performance architecture that a lot of services have adopted. It has to load tenant code and it has to unload it when they deploy a different version. It's pretty old now, and it's using a lot of custom code. It's using open source libraries as well, but also we've developed a lot of special things along the way to make this possible. It also has a lot of dependencies, both direct and transitive, and it happens to have relatively tight performance targets. Our clients are very sensitive if we cause any latency regressions. So all of this put together means it's a complicated, complex application that's business critical and has tight performance targets, meaning it's not super easy to migrate. There's a lot of things that can trip us up, and it's not like it's a toy application. This is business critical and complicated. So that's kind of a little bit about the runtime. So when we wanted to go and move this old, complicated, dependency-heavy thing, we first had to look at, what would move first. And it turns out that the Linux image is the first thing we would need to change. As Frank mentioned earlier, Graviton supports AL2, but we were using something before AL2, AL1. So to even get into the game, we would have to move all of our software from this original Linux image to the newer one. And this is important because we were relying on a lot of built-ins to the Linux image, like libssl, GCC, standard lib, just kind of the basics that underlie all of our software, these core dependencies. So changing that was going to cause a cascading upgrade storm for us that was not really related to ARM, but was in fact going to be a lot of work. And that's going to be a theme throughout this little discussion, is we had to upgrade a lot of things, not really for ARM, just so much for technical debt and hygiene reasons. So I ran a test build, and we got a lot of failures. It wasn't going to be easy, and we were going to have to go through and upgrade a lot of things. Like I said, they weren't really ARM specific. It was mostly just technical debt and hygiene things, which if you've run a service in production for a long time, you've probably had to make trades that you weren't completely happy with for, technical debt reasons, but, got the job done. But now the job was to fix all those to get to Graviton. So we were going to have to clean up a lot of old shortcuts. We had a lot of incidental complexity. And what I mean by incidental complexity is when you're solving a problem in engineering, there's kind of this core problem, right? And if you don't solve all of it, you haven't solved the whole problem. And that's the complexity that's inherent. If you solve it, however, you usually end up doing more work than is strictly necessary, and you end up with extra complexity around the core. This extra complexity is kind of regrettable, and I'm going to refer to it as incidental complexity. Now, there's various degrees of quality of implementation that have more or less incidental complexity. We'd accumulated quite a bit, and we're going to have to get rid of it so that we can move things to Graviton. So when I was looking at this build failure and all these packages that failed, I started to think, what can I do to fix these, or can I get rid of them? And there is a set of about 5 decisions we would make given any sort of failure that we are looking at. First, we'd look at removing it. Maybe we could upgrade it, replacing it, asking for help, or at the extreme end, deprecating it. And these are based on kind of the incidental complexity we expected to remove by taking that action. So if we removed a package, that's a lot of complexity that's removed because that code's just gone. And they're also based on how much kind of return on investment or effort it would take. So removing can be really easy if you get lucky, and it also removes a lot of complexity, so it's a nice choice. I'll go through each one of these with an example to help kind of explain further. So first, remove. This is nice because you can get rid of stuff you don't need, right? Like, you might think that this sounds silly because if it's there, then I need it, but that's not always the case, especially with old applications that have, changed throughout their life cycle. For a lot of things, they evolve, and assumptions that were made at the beginning when these dependencies were taken may no longer be true now. So it's good to kind of audit what dependencies you have and if you actually need them. Depending on your ecosystem for your language and what you're doing, this might be more or less difficult. If you have a newer language with a better build system, maybe you're already doing this by default. If you have an older language that's more difficult to infer dependency graphs, you might have to do it by hand. But it's really worth doing because if you can get rid of code, your maintenance burden goes down and it's easier to move things to new platforms or, processors. So in our case, we had a dependency that was not related to what we were doing called JavaFX. JavaFX is a UI toolkit framework, and we're a backend data aggregator. We don't do anything with UI. So the fact that this was in our dependency graph at all was confusing and was kind of a big hint that something wasn't right. Now, when I looked deeper, and this was a transitive dependency, like we hadn't taken this, but one of our dependencies had, it looked like they were only using one class from that package in one place in some test code. And the class they were using was a generic utility that was not really related to JavaFX. It was the pair class, literally the idea of two things. I looked at it and I realized I could just re-implement this. It's trivial. So I re-implemented my own pair, and I was able to drop the dependency on JavaFX, which is a very, very large amount of code that we didn't need any of. This was preferable to having to deal with taking a new dependency and pulling that code in or fixing whatever else was broken with it. And as an aside, this is a really easy thing to do in Java because JavaFX used to be shipped by default with the JDK, which meant that you were one accidental import in your IDE away from taking this dependency. I was pretty confident that's what had happened here, and this wasn't really something that they wanted, it's just something that had happened. So in this case, code duplication was better, and we were able to drop the dependency and move on. It was a nice improvement in incidental complexity. But sometimes you won't get that lucky, and it won't be easy to just drop a dependency. So the likeliest option you're going to take for most of these failures is probably to just upgrade the package. It can be really easy. A lot of packages are forward compatible, and all you have to do is change a version number somewhere in a dependency file. If you're using modern languages that deal with this for you, you might just have to run a script to automatically upgrade and you could be done. But it's not always that easy. If you're particularly out of date on a package, it's likely that things have changed, either in the API of the library to break your calling code, or in the behavior so that it no longer passes tests or could even break your application. And the risk here kind of grows the more out of date you are, which comes back to kind of the hygiene aspect here. If you haven't been doing your hygiene homework, then there's a good chance that when you upgrade something, you'll be changing a lot of code across a lot of time and things will break. If you're relatively up to date, hey, no big deal, it'll probably work. So in our case, we have a build system for Java and it's internal. And it has a nice upgrade path because the team that owns it understands that everybody's going to have to upgrade this eventually. And so they were able to provide a very smooth experience where all you have to do is change that number. Now, the reason we had to upgrade it is that it comes with a lot of batteries included. And these are things like spot bugs or JUnit, other kind of build tool related things. And because they were coupled to the version of the build system, they had now become out of date. The batteries were dead. So all we had to do was upgrade to get new versions of these tools. And that was pretty easy. You just pull a package, change the number, boom, it works. This is kind of one of the ideal situations for an upgrade, but a lot of things will be this easy. But when things aren't this easy, or at least when they're a bigger piece of code that's scarier, you're going to be relying on your tests. And this is kind of why you wrote your tests, right? For big changes that are kind of around the application or inside of it. You want to validate things still work. So this is where you're going to start getting a lot of benefit out of those tests that you wrote. Now, if you can't do an upgrade, maybe the thing you were using is end of life, or there's some problem where it's just too big of a gap, you might consider a replacement. There are a lot of packages out there that are alternatives for any one other given package. Most libraries have competitors, and there's usually similar functionality. This is more work than doing an upgrade, because you're changing a lot more code, right? With an upgrade, you could be changing a few lines across a version. With a replacement, you're almost certainly replacing all of the code. So it's scarier from a risk perspective. It also probably means that you're going to have to change your calling code because the API is not going to be drop-in most of the time. So this means you'll need deeper testing. But it can be a really nice change, especially because when you first took this dependency that you're looking at replacing, you might have had a different set of requirements, and you now get to kind of reassess those. You get a chance to do a do-over with your dependency. So if you have to change it anyways, it's a good time to consider if you maybe want to learn from your last experience and change some of the decisions you made, some of the trade-offs. So, for example, in our case, we used an internal caching library for a core code path for our customer caches. As part of our hosted experience, you can configure a cache and get some data cached. It's very nice, very easy compared to having to spin up your own service, but it meant that we had to deal with this caching library. And it also meant that it was on the performance critical path. But caching happens to be something that a lot of software needs to do, and so there were many options to replace this particular library, which is just an in-memory TTL cache. So I looked around and I found a few options, and the same team had actually written a replacement. And I got really lucky in this case because that team had written the replacement and it was similar to the previous. The interface was very similar. Not drop-in, but close. I was able to, with just a couple of light spot welds to some adapters, drop it in. And this is going to be more difficult or less based on your application architecture, like is stuff factored out well, is it plug-in, or is it coupled? And it also depends. Some of the dependencies you have will not be so decoupled. They'll have to be by nature integrated to the core. So if you find one of those needs to be replaced, it'll probably be difficult. But this will depend. And you might get away with just a couple of adapter classes like I did. But because this was such a scary change, unit tests weren't going to be enough, right? This was performance critical, core code path stuff. So I ran our large suite of performance tests to validate that everything was fine and did additional integration and spot checks to make sure. And it turned out that not only was it compatible and the same performance in most situations, it was actually slightly faster in others, which is kind of one of those benefits I mentioned earlier. When you're taking a new dependency, you might be able to get some kind of wins for free if you pick the right one. In this case, I kind of just got lucky, but upgrading software often has improvements. So make sure you performance test extra when you're doing core changes with replacements because of the risk, but sometimes you'll get a win for free. Okay, if you can't remove, upgrade, or replace, you're starting to run out of kind of easy options. But you can still ask for help. And I didn't put this first because I think it's worth kind of doing your due diligence here to make sure that before you go out asking the world at large for help, you have a good grasp of the problem. But it's good to leverage your community because there's a lot of things going on in software and probably you don't know everything. So by asking for help, you can learn things that you wouldn't have otherwise stumbled upon. And it's a good time to be asking about ARM in particular. I know most of these changes won't be for ARM, but if you do happen to run into one that's specific, it's a much easier question to ask now that a lot more people are using ARM. So the chance of getting support is good. Just make sure you do your research first so you can ask a coherent question. In our case, we had a native dependency through JNI on some C++ code. And it was pretty out of date. And it was also a core thing to our application that we couldn't drop for business reasons. And there was no upgrade path. So we were kind of stuck. We didn't have any obvious replacements here. I couldn't fix it. I'm not much of a C++ engineer, and the amount of technical debt and age here was going to make it difficult to change. And this isn't to impugn C++. It's just this thing was really, really old. But I asked for help. And it turns out that my sub-use case of what this big package was doing was actually something that the owner had anticipated and re-implemented in Java. There was some serialization that I needed that was a very small piece of this overall package. And that re-implementation in Java was actually drop-in, which is great. That was a really smart thing for the owner of this package to do, or at least nice for their consumers. And it worked out of the box on ARM. So I was able to reduce incidental complexity significantly, as well as avoid a lot of work by just asking for help. And I did have to do a lot of testing because it was a replacement that was scary and there was correctness implications potentially. But I worked with my customer to validate that it was extra super safe and got test data to spot check it, as well as running all of our standard A/B tests. And it was a drop-in, and it was correct out of the box, and it was the same perf. So that was a really nice result I would not have been able to find had I not asked for help. And like I said, it was even drop-in. What more could you ask for? So if you asked for help and it hasn't come, you don't get any good response, maybe they don't answer, or there's no other trick you don't know about, you might consider deprecation. This sounds kind of severe, and it is, but there's a large overlap between kind of services that are difficult to work on and regrettable and things you want to stop having. And, if you can't migrate it to ARM, doing the work to get rid of it now is probably going to pay off and give you more engineering resources back. So sometimes just front-loading that can be worth it. You can take the effort you would have spent on that and use it to migrate something else to ARM. So what do I mean by this, right? Deprecation seems like something that you would never have a chance to do, but we did run into this in our work. There's another internal C++ code base that used a lot of those same packages that we had just avoided by changing that other serialization dependency out. And it pulled in a lot of other code that wasn't ARM friendly too. So this was looking pretty bad. I ran into this and was, running out of options pretty quickly. Now, I'm going to switch perspectives here. The team that owned this package also noticed this, and they had a lot of teams depending on them. So they weren't going to be able to push a migration campaign very easily. It was a tough spot for them as well. But they decided it was going to be worth it. And they actually did a full rewrite and re-architecture of this thing to be much simpler, both for the consumer and them to own, and a lot more performant. And as one of the side effects of reducing that incidental complexity, it now built on ARM pretty much out of the box. So because they decided to do this painful migration campaign, they were getting back a ton of support effort right away. It had taken them about a year to do this, which is always, of course, the right time to start a deprecation last year. But because they had the foresight and committed to doing this work, we now had a much, much simpler support path going forward. I did have to change things in my application. It wasn't drop-in. I had to change some of the runtime architectures. It was somewhat invasive, but it was so much better than running that old service and that old code that it was worth it. So because they decided to do that, I was able to get to ARM more easily. They didn't have to port decades-old code, and both of us got a simpler end result, so less effort going forward. And like I said, I switched perspective there. So from my perspective, it was just an upgrade. But for them, it was a deprecation. So deprecations can definitely be worth it. So in summary, kind of based on effort and incidental complexity shrinkage, you really want to go in order, ideally from remove, because it gives you the best return on investment for complexity, to upgrade. It's going to get the job done. That's usually not too much work. If you can't do those, maybe look at a replacement. Sometimes there's easy drop-ins and it's not so bad. And you can get kind of free wins if you pick the right replacement, but it can be difficult. Asking for help if you've not got any good options yourself. And failing all else, consider some more extreme options around deprecation. It doesn't usually fit, but when it does, it can pay off big time. So those are kind of the low-level things we did. But as we went through these 2,000 plus packages and fixed them building up at the bottom, because you get a build failure and the bottom parts fail and you can't see the rest of it and you work your way up, we learned some sort of meta lessons about doing this process. The first one is even simple work can be hard. So I mentioned upgrading the build system for Java. Any one package, that was easy. I just changed the number, kicked off a test build, and it passed almost every time. But because there were so many packages to upgrade and the overhead with making a change, doing the CR, getting it pushed, built, deployed, validated, etc., was not free. It was difficult to do it for this many packages. So this is kind of the core problem of migrations, right? You're like, well, it's not any one thing, but there's so many changes that in aggregate, it's difficult. So the less you are up to date on your hygiene work, the more painful this becomes, which is why, of course, you don't want to accrue a lot of technical debt, because then all of a sudden doing something that should be easy is hard. But if you are out of date, just be prepared for a lot of small things to pile up. Another thing we ran into was code reuse is good, right? We like taking dependencies because that reduces effort to write code. But at the same time, it can couple you to code in a way that you don't want, especially across teams. Teams may or may not share priorities. And if you share code, then you're coupled to that team, which means if that team doesn't want to provide resources to do an upgrade or do your code reviews, you're going to get slowed down. So ownership alignment is just as important, if not more so sometimes, than code reuse. So think about when you take dependencies, what the maintenance story will be, who will own it going forward, and who will make decisions around it so you can avoid getting teams coupled in ways that hurt. Another thing that we did, because there were so many packages, is we pushed fixes incrementally. It can be tempting when you're doing a migration to just pull all the code, make all the changes, know that you got it done, and then push them all. But we don't do this with standard software development, so you probably shouldn't do it here either. In our case, it was infeasible because I couldn't even see the end before I was done, right? I had to make changes and kind of assume this fix would work, and then occasionally it wouldn't, and back out and take a different path. So you really want to try and make incremental progress so that in case things change or you find that you need to back out, you at least have some save points to go back to. Otherwise, you can just sit there forever kind of churning on this giant build. It's also important not to cause service interruptions. So while we were off doing our migration, there were other teams and developers working to produce features and do other sort of business critical things. And we didn't want to impact them. We had to stay out of the way. By pushing small changes frequently, if there was a problem with the build or a performance issue, it was easy enough to see, well, here's the changes and there's this Graviton migration change, and it's clearly not important, or it's probably the problem. This is just the standard continuous integration, continuous deployment advice, but it applies here as well. Another thing, estimation is an art. When you do a 2,000 plus package migration, and you can't see any sort of line of sight to the end, you won't know how long you have left, either in effort or calendar time. It's really difficult to tell if the next package that breaks will be a 1-minute diversion where you change a build system, or a 3-month diversion where you find an equivalent package, do a bunch of performance tests, and then make sure that it works for all your consumers. And because of that uncertainty for each fix, combined with the fact that you have a lot of packages in migrations usually, and that you can't even test them all at once because builds can't succeed until all of their dependencies have, you have a lot of ambiguity. So you can try and make up for this by doing week over week estimates and burn downs and things like that. But the core thing here is that you don't have high confidence because there's too much ambiguity, and you should report that. Just report that there's a large error bar and that things can change week over week chaotically. It's better to report reality than to slip at the last second for many months, right? People really don't like it when you do that. So make sure that you just represent your uncertainty and that people are aware that this is a big, complicated thing and it's not going to be easy until it's done, right? Okay, we did the build. We got all the packages building. And then finally, we were ready to go on performance testing. And we had planned as part of the migration, and you should too, to have a little bit of time to tweak stuff to get it right. Because out of the box, it didn't work. And this might be surprising for you to hear to talk about Graviton. You think it'd be all sunshine, but there's a little bit of cloudiness here too. And this is just to say, be ready to do some performance testing. When we were doing this, we had kind of two different machine types we wanted to replace, and we wanted to win in two different dimensions. We wanted to be cheaper, and we wanted to be faster. But we were only winning on faster and only for one of the host types. So we weren't going to get this out of the box. So we had to start doing performance tests to figure out why and where was this time going, what was going on. And one of the first things that came up was that as part of the migration, we had been kind of forewarned that JDK 8 wasn't going to be as performant on ARM as it could be, and JDK 11 was really preferred. But that was a whole other migration that we didn't want to deal with. There was enough work already, so we had pushed that out of scope to try and be conservative and get things done. But it was now coming back to haunt us, and it looked like we were going to have to deal with it. So this is something I want to impart. If you're on Java, on the JDK, make sure you're on Java 11 or newer, because without it, your ARM performance will not be optimal. You really want to be on JDK 11. So, okay, we went back and looked at that migration, and we were already getting the benefits of that complexity reduction here because there was a lot less work than when I had initially scoped it. By just upgrading things, most packages were now kind of in the ballpark and worked on 11 out of the box. There were a few things I had to deal with, but moving from JDK 8 to 11 is a whole other talk. Just be aware that it's not as easy as 6 to 7 or 7 to 8 was if you're on Java. But anyways, we went back and we did it, and it took us about a month to get a build candidate. But then when we put that under perf, we got the performance results we wanted. We were winning in all the dimensions, and it was time to actually go to prod. Because until you go to prod, you don't get the money. So now we wanted to go to deploy to save the cache. Of course, we didn't want to do it all at once for the same reason you don't want to deploy software all at once, right? We wanted to do an incremental deployment. And what I mean by that is based on risk and blast radius. So we picked our fleets out, and we have a lot of different fleets and places that we run code. And we kind of scoped them from least risky, like test fleet that other teams test against, where we can't break it all the time because it'll damage the other team's productivity, but nothing in prod cares about it, to the biggest regions and the biggest fleets that cause the website to go down if they're not active. So we started small, and we worked our way up, and as we got more confidence by each incremental deployment where we would watch it run and wash out the risk by saying that nothing was broken, the performance was landing like we thought, we got more confidence to go to the bigger service fleets. And this is also kind of a practical consideration, because if you have tens of thousands of hosts, it's kind of difficult to do an A/B flip-flop deployment. That's just a lot of doubling of host sizes to deal with. So there's a number of reasons to do incremental besides risk, which is just kind of the mechanicals of moving hosts around. So we did it, and we were at over 53,000 hosts for Prime Day 2021. So when I said that we were betting big on this, I wasn't kidding. This was a significant portion of our host count. And I hope that it imparts to you that this is something you can rely on. This was a lot of capacity, and we went through Prime Day with no issues whatsoever. It went very well. And we're continuing this for our Q4 peak, which is going on during this talk. The number is not fully finalized yet because I'm recording this ahead of time, but it should be around 70,000 plus instances on Graviton. And the rollout continues. So we got some money, we saved it, right? Now, what are the actual results? I kind of skipped over that earlier. So I'm going to mention some numbers, but mostly just generalities. The first thing, improved max throughput per host. This is almost certainly largely in part to the non-SMT or non-hyperthreading features. The physical cores really help us under load to continue delivering results consistently without a lot of performance degradation. And that's kind of the second thing. We're more stable under load because we don't have to worry about thread switching out, sharing a physical core. When we try to run a thread, it runs. And that means that we get better contention or lower contention and better stability. We also have better latency, which is related to the contention under load. Things are able to run, they can run immediately, they don't have to wait. The performance of the processor is very good, and so we were able to kind of get all of these nice reliability and stability aspects of performance, as well as the cost savings. So in a raw cost versus the old instances that we replaced, we got about a 22% cost savings. If you combine that with some of those other numbers that I can't share here, it does add up to around 39%, give or take, add or subtract, because of different fleet types and regions and many other factors, to around 39% cost performance. So we got very close to the advertised number, which I was surprised by. Usually you don't land that close to it. And I was very happy also to see that we had successfully gotten what we started out to get. So we've already saved millions of dollars in IMR, and we continue to save more as every day goes by and we migrate more fleets to ARM and to Graviton2. So some final thoughts for you, kind of retrospective on this whole migration. Software hygiene is really important. Most of the work here wasn't ARM specific. It was just sort of paying off technical debt we had pushed aside for too long. The actual ARM specificness was very small. Limit your dependencies. That's why remove was my favorite option. The fewer dependencies you have, the less code you have to move, the less complexity you have, the closer your incidental to your core complexity tends to be, and the less maintenance you have to do, right? Fewer things you have to upgrade. Sharing code with an eye towards maintenance. Whether you're taking a dependency or giving a software library away to somebody else, this is going to imply team interactions. And the more of those you have, the more overhead you have when you need to change things, especially if it's breaking. So really make sure you know what you're signing up for if you're going to share code with another team. Migrations are inevitable. So at least in my org, there's something probably on a yearly basis that's going to require moving a lot of code in some direction, where the more code you have, the sadder you'll be, whether it's for security reasons or for a new processor or some new compliance, or just really there's a lot of things I think you can think of off the top of your head you're probably going to have to deal with. And it's really uncomfortable to have to tell the business, oh, hey, yeah, we'd like to do that, but it takes us 8 months to do anything because of engineering technicalities. If you do your work ahead of time, you can just say yes when somebody tells you to go save 40%, instead of having to go off on this long migration path. So if you're ready, you're agile, and then you can respond to business needs more quickly. This final thought probably isn't going to surprise anybody, but hopefully I've motivated it. Graviton2 offers strong and consistent performance. It's really nice, especially on the consistent part, because under high load, I don't have to worry about things flying away latency-wise or contention creeping up as much. Things just work consistently, and that's really nice for operational reasons. So with that, I'd like to hand you back to Frank. We'll talk about some of the resources you can look at if you're interested in moving to Graviton.
Thank you, Sean, for sharing your experiences and success with AWS Graviton, with one of Amazon's largest internal platforms. Now, I'd like to share a few resources that you can use in your journey with Graviton. This first link provides a link to the EC2 Graviton product page and has more details about Graviton, as well as highlights from several other customers that have had similar success to the DataPath team. The second link is one that you should check out. It's a GitHub repository that has detailed sources that will help developers and teams in your transition to Graviton, including things like details of third-party software support, performance runbook, and much, much more. Finally, thank you. Thank you for your time, and both Sean and I will be excited to see what you'll do with Graviton.